Let me go ahead and introduce RC. He has the shortest bio of the day. So RC is a product person. He is the Defending Democracy. He runs the ElectionGuard program for Defending Democracy at Microsoft. He has worked in many orgs and formations, from Amazon to, in his words, deservedly failed startups. But he ideally always, in some kind of launch capacity, is always involved. So with that, RC, I'm going to, if you can go ahead and start sharing now.
Share now. Let's do that.
And I will queue your share up as soon as I see it. And I will send you live now. So there's about a 20-second delay for everybody who's been in the call today. So if you have questions about ElectionGuard or you have questions for RC, just go ahead and put them in the QA and then we will answer them as they go. So take it away, RC.
Thank you, Scott. Hi, everyone. As Scott mentioned, I am RC Carter. I hope you can hear me. I am Director of Strategic Projects for the Defending Democracy program. So I'm here to talk about ElectionGuard, but I want you to note, ElectionGuard is a Microsoft open source SDK, but we wouldn't be here without the help of the Inferno Red team. Scott, Brian, and Roberto, who have presented today. I think we've worked with almost all of the Inferno Red team at some point over the evolution of ElectionGuard. So we're super happy to be here for this code camp.
Thank you. I appreciate the kind words.
So as I said, hopefully my presentation will advance. Let me go into PowerPoint, make it advance that way. There we go. So I'm going to talk about a few things today. Introduction to who we are as Microsoft and the Defending Democracy program, a quick overview of voting in the US, a discussion of what ElectionGuard is, particularly in the context of end-to-end verifiable elections. We're actually going to learn about homomorphic encryption, which is the technology that ElectionGuard uses to provide the secret ballot capability. And we'll talk a little about the SDK itself, where we are, and then also how you can help. We have some wonderful activities going on this month, also with the help of Inferno Red and a Hacktoberfest to help write verifiers. At the end of this, you'll be all excited about verifiers, we hope. So the Defending Democracy program is a program started by Microsoft in April of 2018. It was in response to a lot of things. And we'll talk about that and how we come after how we view the challenge of help, or the opportunity to help democracies. We have three key pillars that we have work in: election integrity. ElectionGuard is part of the election integrity pillar. We have a campaign security pillar, and also a disinformation defense pillar. I don't need to explain the necessity of trying to introduce security and increasing confidence in elections. 2020 has proven to be even more adventurous than we might have anticipated coming in, especially with the advent of COVID and other aspects going on. So the way we approach helping as Microsoft is we believe that technology can be used. We take a technology optimist view. We want to help. We want to help by playing a leadership role, but mostly through partnerships. We don't want to lead too much. And when we talk about the SDK, you'll understand how that manifests. We also want to be nonpartisan, and we seek to help principally democracies. And people say, like, why does Microsoft have a Defending Democracy program? And the truth of the matter is, companies like Microsoft work much better in democratic societies where the rule of law is observed. So we believe that we can help, and we want to help because we perceive that there are ways we can. When you think about the threat vector of elections, you have lots and lots of small U.S. municipalities facing Russian or Iranian or North Korean or Chinese state actors that are trying to hack their systems. It's an asymmetric threat, and we need to help out. So in the election integrity pillar, we have four key motions we're taking. I am the product manager for ElectionGuard. We'll talk about that today. We also have other efforts led by other teammates of mine. We have the election security advisors, which are really deep dives with specific election technology vendors to take an analysis and security recommendations for their systems. We work with a good chunk of pretty much all the US vendors that are on Azure. We have worked with them. Same thing for Azure for elections. So election security advisors is deep dive security interventions. Azure for elections is more programmatic advanced preparation for elections and review of their infrastructure in anticipation of events. So we've been going through that as well with the election infrastructure in the industry. And finally, we have an election war room, and that's a joint war room. We'll have an East Coast and a West Coast war room, and also we work with the U.S. Government relationships, CISA, DHS, and a whole bunch of acronyms that I'm unfamiliar with, but we actually, and you know, election day is varied now. It's actually 30 days. You can start voting. You have started voting. The election has started in some municipalities, especially military voters. So it's longer than a day, but we do focus intensely. We have teams together on the day of the election, November 3rd, to set up rapid response in terms of what we do in the case of specific events. So within campaign security, we also have multiple actions going on. M365 for campaigns is a custom office set of features that has very discounted price, but it's also a bunch of very simple setup. When you think about campaigns, they're very short-lived websites. When you think about it, organizations that you build, set up quickly and break down. They're typically not manned again by technical folks. So this is a bunch of very simple building blocks that have very high security scores designed around the hacks that occurred in the 2016 election. If you think about all the things that happened to the DNC server, the DCCC server, I'm not sure which one it was, that M365 campaigns was designed around that. Account Guard is similar for Outlook, Hotmail, anybody on those kinds of infrastructures can for free be brought in, especially for if you're a political party, think tank, governmental organization, those who are subject to attack from state actors who use those for password harvesting to get access to campaign officials. So all of those folks are automatically enrolled, and they're actually part of the monitoring that goes forth when we talk about our nation state attacks. In addition, we do campaign security trainings. One of the things that's really important this year, especially for election administrators, is like, what are the building blocks of security? We have 1,500 professionals we have trained, a lot in the US. We've done webinars with the key election officials and administrators. And generally, you know, as I said before, we try to do this through partnerships, Defending Digital Campaigns, the Belfer Center. We always want to be working as part of the community. And then finally, Disinformation Defense, especially, I think we all know this year, the challenge of deepfakes. We have a bunch of threads going on there as well. Video Authenticator, Project Origin. There's a great deepfake quiz. If you want to find out what's going on there, we can go to our website, the Defending Democracy website on Microsoft on the Issues blog. But I'm going to shift now. I'm going to start talking about ElectionGuard and voting and what we're trying to do. So this is a snapshot of voting from a very respected organization called verifiedvoting.org. This is from the Verifier, which is a database of all the different voting machines that are used in the US. And you can see from this, they're kind of biased towards hand-marked paper ballot, but you can see within this, there's a bunch of different systems that exist in the US for voting. There's not one monolithic system. There's three principal vendors that own about 80 to 90% of the market. But even those vendors are made up of a bunch of acquisitions of previous generations of technology. So you can see that in the green there, you have hand-marked paper ballots. That's what the majority of the country is. I'm from Washington. We do mail-in ballots, so that's considered a hand-marked paper ballot. A lot of polling places, you go when you fill out the ballots in person on election day and then submit them into a scanner. That's also hand-marked paper ballot because it's speaking to the way you interact with the devices. There are other types of voting systems as well. Ballot marking devices, and I'll give an example of that using ElectionGuard. We have a lot of these things called direct response electronic, which are actually voting machines that were built after the 2000 elections. We had the challenges of paper chads and hanging chads. Some states still have that technology that they're called DREs. Nevada still uses them. And they're actually electronic devices, and they don't produce any paper artifact whatsoever. And that's a challenge for a lot of audit folks because you have no way of verifying a tally of an election. But the point of this slide is to just show there's a huge diversity of voting types and voting machines and voting technologies that we need to support if we want to actually bring ElectionGuard to the voting populace. So in addition, I think that there's a couple of things when we think about voting, there are a couple of key constraints that we operate within in trying to come up with a solution for this industry. The first and the hardest to solve is the secrecy of the ballot. And that's specifically when we talk about homomorphic encryption, that is fundamentally what is addressing secrecy of the ballot. And by that we mean you should, once you voted, you should be comfortable that your vote was recorded correctly. But once you voted, you can't pull it back. You can't have any artifact to show what you voted, because if you did, you'd be subject to collusion, right? That's the value of the secret ballot. You should feel unencumbered, or you should feel no pressure to vote for any particular candidate for fear of them discovering your vote. So that's a very, very important constraint. And when you think about security, a lot of people think like, why can't election security use a lot of financial security? The challenge, the fundamentally different, because with financial transactions, you can verify that transaction is supposed to be visible to you. In this case, the transaction is not visible to you. So how do you build integrity? How do you build confidence in the integrity of a system that you can't see the ballot that you submitted? It's fundamental. So we'll talk about that. And then also privacy of the voter. You know, just as well we can't see what the contents of the ballot is, we can't know who submitted that ballot. So very important issues. So the way we solve it, or we're hoping to help solve it with Microsoft and ElectionGuard, is this notion of end-to-end verifiability. So I'm showing a paper here from 2015 just to show the kind of the folks that are working on this problem. In truth, Dr. Josh Benelo, the Microsoft researcher whose technology ElectionGuard is based on, is really with some of the major figures of cryptography. You can see Ron Rivest there is one of the godfathers of cryptography. Vanessa Teague, she's the person. There was one other kind of claimed end-to-end verifiable system put out by Swiss Post. Vanessa Teague showed that it was not and hacked it effectively. And this is very intense math, but very respected cryptography. So that's what we're building ElectionGuard is. So when we talk about ElectionGuard, we're talking about the notion of end-to-end verifiability. So what is end-to-end verifiability? And it's really a set of voting principles. It's a set of ways voters interact with voting systems and the creation of particular artifacts and capabilities that allow them to feel confident that the vote they cast, however method they cast it, was both captured correctly and participated in the count. And we have to do that in the secret ballot framework, right? So there are three principles. Voters can obtain assurance their vote was properly recorded. That's very important. We'll talk about that in the ballot marking device example. Voters can verify their ballots have been included in vote tallies. Right now, you can get verification that your vote was delivered, like in mail-in ballots. It's hard to extend it all the way to being included in the tally. That's a principle of end-to-end verifiability. And finally, that the public can verify that the final tally is the correct result of all the ballots collected. That's the other aspect. You publish all the voting artifacts, and then you release tools, or tools are built to verify that those artifacts are correct. The fundamental problem we're addressing and trying to change the dynamic of around elections is, instead of, what we do right now is we put a lot of security restrictions on the voting systems themselves and hope they were correct, and hope that there were no hacks. What end-to-end verifiability does, it allows you to release the records in their encrypted form. So you have to maintain secrecy about it. You cannot just publishing the records, but you release them in a way that allows them to be independently verified that the tally was correctly obtained. And because it's public, the scrutiny shifts from verifying the results of the election instead of the security of the systems. You still have to maintain, obviously, security of the systems, but the proof is in the pudding of the published results. That's what we're trying to accomplish. And these sets of principles ensure that published result is accurately reflects what happened in the voting booth or when they mailed the ballot in. And I realize there's a lot of stuff here, so feel free to ask questions. But those are some fundamental kind of components, what we're trying to solve with ElectionGuard. And there's four key aspects to an ElectionGuard election, right? So there's a key ceremony. That's the beginning of the ceremony, where we actually use a bunch of independent guardians to convene, create private keys on their own, share their public keys, and this ceremony takes each of those independent public keys and synthesizes them into a single public key that is used for the next step of the encryption of the ballots themselves. The reason we do that, we have multiple actors here, because you don't want to have any, there's just one admin that had that access, then they can do everything. So we use multiple actors there to distribute the security across all those actors, and they're all independent. The whole point is that they're independent. They would include to kind of unveil or release the results. They generate a synthesized public key that is used to encrypt the ballots that the voting devices are. In this case, could be a scanner or a ballot marking device. Then we take those results out, generate the tally in the systems, and generate the artifacts to publicly generate the result. That's the entire ElectionGuard SDK. And so when you think about how ElectionGuard might manifest in an election, let's take, this is an example that I use. It's very simplified. This is supposed to reflect simplified results. So in the top left, you see, we'll call it a ballot marking device. It's just it's an electronic device that allows you to fill out an election form, a set of ballots, and then you hit submit. When you think you're done, presented with a summary screen. And when you see that summary screen, you say, okay, I'm going to ready to print my ballot. So this is important from a structure. I've seen a summary screen. I'm going to print my ballot. So the voter has made the decision that the ballot correctly contains the information they want. That's an important element of end-to-end verifiability. They hit print or print ballot. So what happens at that moment? Obviously, we print the ballot because this is going to be this is a ballot marking device that prints a ballot that is scanned by a scanner. That's where the tally occurs. So this is the printing of the paper ballot. When that paper ballot is printed, we send the results of that ballot to an ElectionGuard instance on that device. That's not a server in the cloud. This is a local. These are all air-gapped devices. These are not. I'm going to check my time. Okay. These are not online. They're intended to be completely off the internet. So this is running locally. So when that ballot is submitted to the ElectionGuard server, it will encrypt the ballot using that public key generated by the key ceremony, and in return, a verification code. That's an important element because that code is what the voter is going to use to, when the results are published, check that that ballot that they just submitted was included in the public tally released later. So, and that has to occur after the voter has submitted their ballot. That's an important element because we want them to make sure that that ballot reflects their final choice. Okay, so then the ballot is printed and the verification code is printed. The voter gives the ballot to the election official and then it is tallied and then eventually released. And they take that tracking ID home because they're going to look that up later. And this is what happens. So like this is the actual verification code that we generated in Fulton, Wisconsin. We had our first election this past February before all the craziness started. And that was printed along with the ballot. So this was done. And when the sites, and you can go there now, fulton.electionguard.vote, the voter would go and start entering that value into a web form, just like a search box, and see that their vote was counted. And that's one of the other key elements that we talked about for end-to-end verification. So I hope that makes sense. It's a lot to absorb, and it's not going to get easier because we're going to now start talking about what homomorphic tallying is. Because I think it's, I love this Arthur C. Clarke quote, any sufficiently advanced technology is indecipherable from magic. And sometimes homomorphic tallying feels that way to me. So I thought we'd talk, this is one of the examples that Dr. Benelo uses to kind of convey how this happens. How do we do this? So because there's a lot of, homomorphic encryption is actually very complex. And although we use it, we can think of it as using a very streamlined, optimized version of homomorphic encryption. And what we mean by homomorphic, it's really important. A homomorphism is a map between two algebraic structures of the same type that preserves the operations of the structures. That's really important. And in this case, the algebraic structures are the unencrypted ballot and the encrypted ballot. And we want to make sure that they are actually the same and that they map to each other and that the operations that they perform are also the same. And what's nice about this, the only operation we really perform in voting is addition. Thankfully, it's the easiest of the mathematical operations, and so we take advantage of that. We also take advantage of the unique structures of voting, of votes, to do this, right? Because ballots are really very simple series of zeros or ones, if you think about it. Like, think of the first race, could be vote for one of four of candidates. For the second race, one of two. For the third race, you don't vote for any, but it would have been, you had a choice of three votes. That's what a ballot is. It's a bunch of zeros and ones. So a lot of the encryption and a lot of the proofs that we generate rely on the fact that it can only be a 0 or a 1, and that a ballot has to follow rules of encryption or just a structure, right? You can't have a 2 there. You can't have a string there. You can't have a letter there. You have to have a 0 or a 1. So imagine now, this is how we typically run a ballot, right? You have Alice has voted on Bob, Carol, David, Eve. Each have voted on the races, and there's a summation, is the total of the candidates receive in each race. With end-to-end verifiability, each of those ballots will be encrypted individually at the voting booth. When the election is over and the ballots have been extracted from all the voting devices and inserted into an administrator device and aggregated, this election administrator device creates an encrypted tally from the encrypted ballots, right? So it's building the parallel structure that we talked about in the homomorphism conversation. What that election administrator then does is she or it decrypts the tally, the final tally, not the individual ballots, the final tally. That's going to be released. So the encrypted tally and the unencrypted tally will be publicly released, and the encrypted ballots will be publicly released. So how do we make sure now that the individual ballots, the individual encryptions, sum to that tally? That's what we're going to generate. That's what these guardians, that when the ceremony is, when the election closes, the guardians get together the same way they did at the beginning. They announce themselves to the administrator device and say, we're here to do the tally. They all each identify themselves, and then the election administrator delivers partial decryptions for them to review and generate zero knowledge proofs from. Non-interactive zero knowledge proofs. So that's the key point there. We have to know that the ballot was correctly formed. We're going to use those to do that. So each of the guardians does it, and they're not doing this, they're just running routines. They're not really doing these calculations themselves. You don't have to be a super brain. It's going to be a script that effectively runs on your behalf, right? So when these partial decryptions and knowledge proofs are done, and each of the guardians has to verify that the decryptions, the partial decryptions that were sent down to their device resolve and the proofs that are generated resolve correctly, no errors are generated, they are then published back to the election administrator. That's what's going to be also part of the structure. If there are errors, then we have to resolve those. But we're assuming the happy path here, that there are no errors, therefore no fraud, and then therefore they can be published. So that's what happens here. The partial decryptions are published, and that's what people verify against. And so we had our first election in February 2018 in Fulton, Wisconsin, and we performed this process on 398 votes and directly matched the tally from the tally machine as well as the hand count from the Fulton poll workers, and that became our tally. We published that eventually into the ElectionGuard site. So that is ElectionGuard. I hope that made sense. If there are questions, I look forward to hearing from them. I can't imagine there aren't. But I wanted to kind of, before I finished off, I wanted to kind of say, like, you know, this is an active project. We are seeking participation. We are seeking help. You know, we are very big supporters of the notion of coordinated vulnerability disclosure and public scrutiny of a lot of our code, like especially ElectionGuard. This is we want to make sure that we have no errors. So we work with the Microsoft Security Resource Center, and a group within Microsoft that does a lot of the nation state attacks that you talk about. We set up a bounty program for ElectionGuard, and you can check it out. You can just search for ElectionGuard bounty program on your favorite search engine, and you'll see our site. It defines the ways that we're seeking help. And if you find bugs, there's a process to follow to do so, vulnerabilities. And we've already paid out about $34,000 already in bounties, and they found significant, obviously the more serious the vulnerability, the more we pay you. It's patterned on the same price that you pay for Azure bugs. So like we said, we paid out $34,000 already, and it helped accelerate our decision to move from our C repo to the recently released Python repo, authored by the Inferno Red folks. So that's an active, ongoing program. We welcome your scrutiny. I think if you want to get involved in the very immediate near term, this is a really fun time to get involved. The Inferno Red team has spent a lot of work building a Hacktoberfest challenge, and it's really about creating verifiers or reviewing verifiers. We have some very simple steps to kind of verify your math. We can set up and run your own environment, and you can decide to help solve. There should be some errors in the verifying bugs that you see, and the data set that you have, as well as taking verifiers and writing them in a different language. I can't wait to see the first Rust verifier, or perhaps Golang, or Cloture, or Jenkins. Whatever your interest is, come check it out, help us out. This is something that could help democracies. We expect to make these available to third parties to use to review elections when they happen in towns near them. So I hope you found this interesting. Thank you again for the time. Thanks to Inferno Red. I didn't want to take too long. You guys have been at it all day. If there are any questions, happy to entertain them now.
Great, thank you, RC. So if there are any questions, please go ahead and post them in the Q&A part of the team's event. We also have the track, etc. Channel in Discord. I've also just dropped the link to the Hacktoberfest screen that you're seeing right now. The bounty program, RC, I think you may be able to drop the link as an announcement yourself in the Q&A. Sure. Okay. But we'll also post these in the track etc. channel in Discord. So are there any questions at all for RC? And we know there's a delay, so we will wait a few minutes or a few moments.
Instead of that awkward 3-second, it's going to be that awkward 20-second pause. So
no, that's okay. I appreciate it. For those of you who don't know, RC mentioned Inferno Red a few times. I'm the CEO and co-founder of Inferno Red, and we are incredibly busy and proud and excited for the work that's been done on ElectionGuard. And we have been very, very focused on integrating ElectionGuard into platforms this year, as well as working and building the core components of this open source platform. And I stress to you, it is open source. So if you're curious, go to the repository, download it, check it out, look at the code, and you'll see. So, okay.
Also, I'm holding up this month's Wired article. So if you actually want, there's a good story of U.S. elections, of which ElectionGuard is the origin story, perhaps, of ElectionGuard and verifiability. Perhaps it's an interesting read if you're curious at all.
Oh, nice. Okay, excellent. All right. So with that, RC, I will give you a chance to just check in on the Discord server, and I will queue up the music, and appreciate you taking the time.
Thank you, guys.
And you can drop off whenever you are ready.